So far, we have talked about optimization, which was easy, which was convex optimization, which basically meant we can solve those problems rather easily. However, sometimes we have problems which are difficult to solve because they are nonlinear. And actually, the best way to solve them is to think hard and think whether we cannot replace those nonlinearities by linear functions. And if we cannot do that, and sometimes we cannot do that, we have to use nonlinear constraint optimization. And here actually the important point is that we have constraints. Because if we don't have constraints and we have nonlinear objective function to be minimized, we have already covered a couple of methods which can solve these kind of problems. So depending on whether we have the analytic gradient available or not, or at least the estimation of the gradient, then if the gradient is available and if it is the system of linear equations, that's easy to solve, right? We just set the gradient equal to 0 and we compute the optimal solution. If the gradient is nonlinear, we can at least use gradient-based methods like the Newton method. If the gradient is not available at all, then we at least have those gradient-free methods. But the point is that all these algorithms, they only work in the absence of constraints. If we do have constraints, the situation is much more complex. And unfortunately, especially in chemical engineering, when you want to optimize the operation of a chemical reactor, where we know that those terms which appear in the dynamics are strongly nonlinear. We have like exponents of the inverted value of the temperature. Okay, so we have two nonlinearities simultaneously. Okay, those kind of problems, they require being solved as nonlinear optimization problems, and then when we add constraints, the situation becomes much more messy. Okay? But before that, let me just remind us what the gradient-free methods were. So we were considering random search methods, like the Lucy-Acoline simulated annealing, or we might have used the approximation of the gradient kind of approaches, where we can use either extremum seeking or the Nelder-Mead method. Okay? But yet again, all these methods, they just work in the absence of constraints. Now what we want to look at is how to solve optimization problems where we are minimizing objective function which is potentially nonlinear and potentially non-convex. Now, nonlinear does not automatically mean non-convex. A quadratic function is a nonlinear function, but it is a convex function. Okay? And we know that minimizing a quadratic function is easy. The reason I'm saying this is that people are often confused, and sometimes they say, I have a nonlinear optimization problem, therefore it is difficult. Not every nonlinear problem is difficult. Quadratic problem is nonlinear and it's easy. Okay? So be careful about this. So we are assuming that this objective function is nonlinear and potentially non-convex. And we have constraints in this aggregated form. And yet again, we are assuming that these terms here, those functions g and h, they might also be nonlinear and non-convex. Actually here, it is enough to assume that they are nonlinear, because it doesn't matter whether they are convex or not, they are difficult. Okay? So let's assume we have a nasty problem, and we would like to find the optimal solution. One option, which we can always use, is the Karush-Kuhn-Tucker method. We can just write the necessary conditions of optimality, and then we can solve those. But there are two problems here. Problem number one is that we know that for a non-convex problem, the solution of the KKT conditions are just necessary for the existence of the optimum, meaning we might have a solution which satisfies all conditions, and it still doesn't have to be the optimal solution. And the other problem, which is closely related to the first one, is that to find the optimum, we have to enumerate all possible combinations of constraints. And we know that we have very, very many combinations to be evaluated. Imagine that n over k n choose k, the n factorial over k factorial, blah, blah, blah. A huge number, okay? Huge number of combinations. Essentially, it's an exponential complexity in the number of optimization variables and the number of constraints. So you don't want to use the Karush-Kuhn-Tucker method to solve these kind of problems, though sometimes it is used, because it's a fairly straightforward approach. So that's why today we will cover one possible way how to solve nonlinear, non-convex optimization problems of this form, which is called sequential quadratic programming. Essentially, what sequential quadratic programming is that we will iteratively solve a quadratic approximation of the problem. So something similar what we did in the Newton method. Also in the Newton method, we were solving approximations of the problems and we were iteratively improving the solution. However, the Newton method didn't include constraints. Well, it could have included the equality constraints if they were linear, that was easy. But if we have inequality constraints, then the Newton method just doesn't work immediately. We have to use the active set method for that. Or if we have nonlinear equality constraints, then yet again, the pure Newton method is not directly applicable. Okay? So the sequential quadratic programming will solve this problem by iteratively doing quadratic programming approximations of this problem. Now, before we continue, I have to warn you, before you start to be too enthusiastic, this method is just a local optimization method, which means it can be stuck in a local optimum of this non-convex problem. But, I mean, these problems are terribly difficult to solve. Even finding one of the optima, even if it is not the global optimum, is very often good achievement. Okay? So even though we have no guarantee of finding the global optimum, at least we have some kind of local optimum. So let us take a look at how this sequential quadratic programming works. So as we said, we will iteratively solve a QP approximation of the non-convex problem. Now, can somebody tell me how do we approximate a function? Like, I have a function. Okay? Let this be x, let this be f of x. When you hear the word approximate a function, what comes to your mind? How can we approximate a function? If you recall linearization, what was really linearization about? Linearization means I pick some linearization point, call it xs, and then what? Then we linearize this function f around this point. Essentially, we are making an approximation of the function around this point here. And in this case, it is a good approximation in a close neighborhood of this linearization point. Otherwise, it's a very bad approximation. Okay? So how could we find the parameters of this approximation here? S of x. How is that function defined? How is the approximation of fx around that steady state, around the linearization point given? Which technique do we use? We use the Taylor expansion. How is the Taylor expansion defined? So first comes the function value at the dead linearization point, and now what? First order Taylor expansion. What is really this? That's the derivative of the function at that point. So we make the derivative of the function. Where? At which point? We have to evaluate the derivative at certain points. So that would be at that linearization point times x minus xs. Right? This is the first order Taylor expansion. But there are also higher order Taylor expansions, right? So what is the second order Taylor expansion? What do we add here? Do you remember that? Second order derivative at that point times x minus xs squared. But there is something more. There is 1/2 here. And actually, the nth order is 1 over n factorial times the nth derivative evaluated at this point times x minus xs to the power of n, right? Okay. The reason why we might want to consider not only the first order Taylor expansion, but also the second order Taylor expansion, as we see here, is that locally we can approximate the function much better by a quadratic function. Actually here, a much better approximation of this original function f would be this function, right? That's far better approximation than the linear function. And this dashed quadratic function is the second order Taylor expansion of the function f around this linearization point. And that's precisely what we are going to do here. Because remember, the whole term says sequential quadratic programming, which means we are going to convert that nasty nonlinear non-convex problem into a convex quadratic programming problem. To convert that, we have to obtain a quadratic cost function and linear constraints. Now, this second order Taylor expansion is basically a way how to obtain the cost function. So instead of minimizing the nonlinear non-convex function, we will assume that we have some linearization point. Well, linearization is not the right term here, because we are not going to take the linear approximation, but we are going to take this as the current iteration. And instead of this non-convex nonlinear function, we are going to minimize its quadratic approximation. So here we are going, this will be now the function that we are going to minimize, right? So we are going to minimize f of xs plus the first derivative xs times x minus xs plus 1/2 f second derivative xs times x minus xs, okay? So what we have done is we have done a local quadratic approximation of the nonlinearity. And similarly, we are going to linearize the constraints. What is the linearization of the constraint g? And here we really mean the linearization, meaning the first order Taylor expansion. So what is g of x roughly equal to in some neighborhood of xs? That's g of xs plus the derivative at that point times x minus xs. So subject to g xs plus g derivative xs times x minus xs. That should be smaller than 0, and actually very similar for h. Now, why are we doing this? What is now the type of these constraints? Remember, g was some very nasty function. Imagine g of x is, just for the sake of the argument, sine of x. Right? Solving a problem which says subject to constraints of sine of x less than 0, well, good luck with solving that problem, because it is a non-convex constraint. Okay? However, what is this constraint? So we have sinus xs plus the derivative of sine is minus cosine, or the other way. So here we have minus cosine of xs times x minus xs. What kind of constraint is this with respect to those optimization variables which are x? These are linear constraint, okay? So what we have done is we have found out like a local approximation of that nasty problem by a very nice problem. Okay? And actually we should be more advanced than just the basics here. We know that the optimization variables, those x's here, they are vectors. So actually we cannot just use the first and the second derivatives, but we must use what? What is the extension of a derivative to vector functions? What is a derivative of a vector function? How do we call that? That's the gradient. What is the second derivative of a vector function? That's the Hessian, okay? So actually we should write it like this. So we still have the value of the function at that linearization point. Now comes the gradient evaluated at that point times x minus xs plus 1/2. And here, actually, we know that this is a Hessian. By the way, here, sorry, I forgotten the power of 2. But since the bracket here is a vector, we cannot just do a power of 2, so we must do it like this, A transpose A, right? So we must write it as x minus xs transpose times the Hessian evaluated at that point times x minus xs. And here the constraints are the constraint evaluated at that linearization point plus the gradient evaluated at xs times x minus xs. That's smaller than 0, and actually for equalities we have the same thing. Okay. So this is what the local quadratic approximation of the original nonlinear problem is about. Okay. We have done the local quadratic approximation of the cost function and the local linear approximations of the constraints. And now comes the conversion. So here, instead of this nasty problem, we solve a much easier problem. It's just that this problem changes depending on the linearization point. And this is where the sequential term comes into play. We actually have to solve a sequence of these problems for improving value of this linearization point. Okay? So we start with some feasible initial point, such that it satisfies constraints. We solve this approximation with respect to x, and we find the new solution. And if it is good enough, we abort. If it is not good enough, then we just set it as the new linearization point for the next iteration, and we just repeat. Okay? So far it's quite easy. There is just one little big problem, and that little big problem is that this Hessian here, we know that for quadratic programming, the Hessian has to be positive definite, or at least positive semi-definite. The problem here is that the Hessian coming from this nonlinear function can easily be negative definite, or it can be indefinite. Actually, what that means is that we are here at this point. Let me see if I have a different color. Yeah. We are at this point. That's the current iteration. And we would like to make a local quadratic approximation of this function at this point. Of course, a local quadratic approximation based on the Hessian is this function. That's the local quadratic approximation. The problem is we cannot minimize this function, because minimizing a concave function is a non-convex optimization problem, meaning very difficult to solve. Minimizing this function is easy, because we are minimizing a convex function. Minimizing this function is extremely difficult. It's basically the same as solving the original problem. And since it can happen that the Hessian sometimes is negative, we actually have to make it always positive. And the way how we make it positive is that to the Hessian, we just add some identity matrix multiplied by a corresponding scalar. Essentially, what we are saying is that the smallest eigenvalue of this bracket here must be at least 0. In our case, what it means is that, yes, this is the problem we would like to solve. Now, what is the best convex function which approximates the original function at this point here? Well, this is a local quadratic approximation, right? It's a very bad approximation, but it is still a quadratic approximation. Okay? So essentially, we are flipping this concave function once it becomes convex. And actually, we only need to flip it such that it becomes a linear function, in which case all the eigenvalues of the modified Hessian would be 0. Okay? And we will see that also in the example. Okay? So Never forget this step. Always make sure that the Hessian of the local QP approximation is always positive semi-definite. Never solve a QP problem where you have negative Hessian. Again, the solver might sometimes give you a result, but you should not trust the result. So the example that we want to cover quickly is the following one. We have a nonlinear function, which is a polynomial, and we have constraints. By the way, what is the linearization of a linear constraint? So we have two constraints, right? The first one is x smaller than 2, and the other one is, in the standard form, x minus 3 is smaller than 0. If we want to find the local QP approximation, we have to define the function g of the constraint. What is g here? How can we write this as g of x smaller than 0? What should be g of x? The g of x in the first constraint is x minus 2, right? What is the linearization of this constraint? Linearization is not 1. Look here, okay? So let's assume that we are at some point xs. We know that the constraint, we are going to linearize this constraint as g of xs plus the derivative, since we have only one optimization variable, times x minus xs, and that should be smaller than 0. Okay? G of xs is what? xs minus 2. That's this term. What is the derivative of g? That's 1 evaluated at xs. What is that? G of x is just 1. Evaluated at xs is still 1 because x doesn't appear here, so that's plus 1 times x minus xs. What is that? Actually, what? So we have xs, we have minus xs here. So we have just x minus 2 smaller than 0, which is the same as before. So linearization of a linear constraint gives us the same constraint. Just some basic math, okay? And the Hessian here, I mean, that's just the second derivative right here, okay? So here is how the procedure works. We pick up some feasible initial point, say this one. At this point, we make the local quadratic approximation. But the problem is that we would obtain this red line as the local quadratic approximation. And since we know that in the local problem we are going to minimize, we cannot actually minimize the red function because it is not convex. We have to change its Hessian such that it is at least 0, and 0 Hessian means we have a linear cost function to be minimized. So now the problem is minimize the green function subject to these constraints. Where is the optimum? Minimize the green function subject to x being between minus 3 and 2. Where is the optimum? Minimize the green function. Go along the green function as much as you can until the constraints stop you. So the optimum is at 2. That's where this green function achieves its minimum. Okay? And that's the new point for the approximation. So at this point, we again compute the new Hessian, the new linearization of constraints. Actually, we know that the constraints will be the same as before. So we just compute the new Hessian evaluated at point equal to 2. And that's the new QP approximation. In this case, the Hessian would be positive definite, so we don't need to modify it any further. And now, minimize this quadratic function subject to these constraints. Where is the minimum? Right here. Okay? So that's the new iteration. At this new point, make a new approximation. Again, optimize, find a new point, make a new approximation, and iterate until we converge. So essentially check the x from the previous iteration from the x from this iteration. If the difference is small, we have converged. Okay? By the way, what we see here is that by starting from x equal to 0.5, we have converged to a local optimum. This is unfortunately the consequence of this scheme. Okay? If we would start from a different initial condition, that this is the local quadratic approximation, again we cannot use this one because it is not convex, so we have to at least make it linear. Minimizing this linear function here would give us this point, -3. At this point we make this quadratic approximation, minimize this quadratic approximation, that's an easy problem. We find this point, which is roughly -2.5. At point -2.5, make a new approximation, which is this one, minimize the approximation, and improve until convergence. So that was a little bit too far, but until convergence is here. Okay. So that's pretty much sums up what I wanted to share with you today, and yeah, that's it.